All right, well, hi everybody. My name is Fraser Kane, and I'm the publisher of Universe Today, and this is your weekly space hangout for April 19th, 2012. This week on the Hangout, we're going to be talking about the recent gigantic solar flare, the search for rogue planets, how to capture a dragon, the big space shuttle Switcheroo, and the end of dark matter. With me, as always, I've got my space friends. I see Ian O'Neill from Discovery Space. We've got Nancy Atkinson from Universe Today, and Dr. Pamela Gay from Astronomy Cast and the Southern Illinois University, Edwardsville. All right, hi everybody. So let's start with you, Ian, and let's talk about. Oh, and if everyone didn't know, I was just on a sort of epic European vacation for 3 weeks in Amsterdam, Paris, and London, trying to spend as little time as humanly possible using a computer. So I think I was quite successful with that. And now I'm discovering all of the new features and functionality of the Hangouts on Air that happened while I was gone. So if I mess something up, I blame it on my old world steam-powered experience with this technology. But anyway, so Ian, you are the doctor solar physicist in the group, and so you are perfectly positioned to talk to us about this gigantic solar flare that was hurled earthward just a few days ago.
Yeah, it was directed more towards Mars and Venus, I believe, and it wasn't a big event. It was on the solar flare scale side. You're talking a medium class flare and a small medium one at that. It was a M1.7, I think. So it wasn't spectacularly big, but the flare flared on the limb of the sun, and it actually triggered a coronal mass ejection. And the coronal mass ejection is a bubble of magnetized plasma that's ejected into space. And of course, that can cause all sorts of trouble if it hits Earth, because it can create a massive electric current through our atmosphere and can short out power grids on the ground and can knock out satellites, of course. But this one, it was directed more away from us, more towards Mars and Venus. And as I say, it wasn't a very big event, but it was a beautiful one. It was a classic looking, if you had to draw a coronal mass ejection, I suppose you would do this. It was basically a bubble which blew out and it was pushed into space. And probably the most amazing thing about this, and of course we got the Solar Dynamics Observatory, NASA's solar telescope that's currently looking at the sun, and it does it in high definition, so we've got this amazing ringside seat of all these kind of phenomena going on deep inside the corona. We're able to see with great detail this coronal mass ejection being blown out into space, and then you suddenly see these funnels of plasma coming back down into the surface. So basically the gravitational field of the sun pulled this plasma back into its lower corona, and it hit the surface. And now these blobs of plasma, probably bigger, each blob looks tiny on the screen, but of course these things are huge. They're bigger than planet Earth. But these things splattered down into the sun's chromosphere and photosphere, basically the solar surface, and it created these wonderful little flashing events. Now, this is actually called coronal rain, and it's actually plasma which is like several tens of thousands of Kelvin in temperature, so this isn't your average rain. This is plasma, really searing hot plasma hitting the surface of the sun. Now, this has kind of posed a few problems for solar physicists in recent past, certainly before we had the SDO to look at the sun for us. Physicists didn't know why this rain falls so slowly onto the surface of the sun, because it follows the magnetic field lines, because of course it's a highly magnetized region when you have an eruption of a coronal mass ejection. So these fibers of magnetism push out into space, and of course the plasma travels along these tubes of magnetism, and for some reason these blobs of plasma were traveling too slow. It was actually raining down to the surface, but it should be happening a lot faster. But with the help of the SDO, in fact, it was only a few weeks after first light, I think it was in 2009 or early 2010, the SDO noticed that the reason why they're going so slowly is because these blobs of plasma are hitting dense regions of gas which are sitting in the lower corona, actually slowing it down. So it almost acts like an atmosphere, actually slows these droplets of plasma down. So there's a lot of really intricate stuff going on with this eruption. And although this was a very small flare and a fairly medium-sized coronal mass ejection, it was certainly a magnificent event. I wanted to try and get the video up, but I can't seem to share my screen. So, but yeah, that's really the news. You have to have a look. It happened on Monday, and yeah, the SDO on their website, they've got some real high-definition video of the event. It's really, really cool.
Do you have a link to the video on your article on Discovery News?
Yeah, if you have a look on discoverynews.com, look at space, and scroll down the screen. I think I published an article on Tuesday, so have a look there.
This is one of the scientific fields that has just really expanded with these wonderful pieces of technology. I mean, would it have maybe changed your education? Because this is where you got your PhD, right, was in solar physics. And so it feels like a lot of the technology to really help just answer some of the bigger questions in solar physics kind of have been pouring out in the last couple of years.
It's really sad, yeah, because I got my PhD in coronal physics. I was looking at the coronal loops. Basically, why are they so hot? Why is this coronal plasma so hot? Because it's the sun, it's hot, but why is the atmosphere so much hotter than the solar surface? And this is called the coronal heating phenomenon. And we've been wrangling with this for like decades. And it's only recently with these high-definition observatories like the SDO that we're able to see these tiny structures in the corona and able to see what could be heating the corona. Now, with the SDO, of course, it was launched in 2009. That was 3 years after I graduated. And a little bit before that, I think it was in 2007 or 2008, one of my colleagues in solar physics actually detected these waves acting in the lower corona. These are called alphane waves. These are basically waves that travel through magnetized plasma. And in my thesis, the theory of our group in Aberystwyth University was that these waves could heat the corona. But we had no observational evidence. We just thought they were there. We know that alphane waves exist in magnetized plasma, but we've never observed them. And so with the help of these really advanced observatories, and especially with the help of the SDO, we're able to see evidence of these waves. And as it turns out, we may have been right, because these waves are actually interacting in the lower corona, and we believe they may be behind the heating and acceleration of the solar wind. So really exciting times, but it's kind of cool being on the reporter side because I got an overall view of everybody doing it. Whereas, of course, when you're in research, you only care about your stuff, and you're glued to your research, and you're very unaware about what's going on the outside. But so it's nice to be on the outside for a change. But yeah,
well, when it comes to solar physics and 2012, you're my go-to guy for sure.
Yes, absolutely. Don't forget 2012.
And then I think you've got a brief piece of news that I think is important, which is that you, I believe, you have your own personal telescope now.
Oh, it's mine. Yes, my telescope. As you probably know, I'm not a practical astronomer by any means. I know how the universe works. I don't know how to actually see it. So we've got in Discovery Channel, we've just got news that at Lowell Observatory, I mean, this project's been going on for a long time, but it hasn't really been spoken about very much because, of course, when you build stuff, it's only when you start discovering stuff things get exciting. But the Discovery Channel telescope at Lowell Observatory is now completed. Now, this thing's huge. This thing's going to be observing the universe in optical and near-infrared light. So it's going to be probing deep into the Kuiper Belt. It's going to be looking at how dwarf galaxies form. It's going to be doing all sorts of crazy science. And it's just been completed. It's a 4.3-meter telescope. It's actually the 5th largest optical telescope in the continental United States. And it's called the Discovery Channel Telescope. And I think that's pretty awesome. And it's mine.
I know. So now finally you'll get a chance to learn. You're probably just waiting because you wanted the right technology to come along before you.
Absolutely, yeah. I don't want to mess around with these small scopes. No, screw that now. Yeah. I'm going to go to Flagstaff soon and hopefully test drive the thing. So yeah, so have a look at Lowell Observatory's website. We also did posted a pretty cool slideshow today, and it's at the top of space on discoverynews.com. Have a look there, and you'll see this thing as it was being built. And it is huge. I mean, this project was massive.
More telescopes are better. And so thank you, Discovery, for throwing in the funds and helping get this thing built. That's fantastic.
Absolutely.
All right, well, so let's move on to my partner in crime, Nancy Atkinson from Universe Today. And you've got a couple of stories, which are news to me because, like I said, I haven't even been looking at computers for the last couple of weeks. So apparently people are searching for rogue planets. Yeah.
Over the years, And I think it's just crazy that they actually do exist, but they've been called rogue planets, nomad planets, runaway planets, orphan worlds, all kinds of things. Basically, these are planets that have been ejected from their solar system, and usually scientists think that this happens through gravitational interactions between planetary bodies. You know, we know that planets tend to migrate in towards their star over time, and as they plow through the material that's in the solar system, any planet between them and their star will be affected, and some could actually be ejected from their orbit around their star. And last year there was a microlensing study that actually found about a dozen or so of these rogue worlds. They were about Jupiter-sized. And from that study, they estimated that there could literally be billions of these planets roaming around our galaxy. And they estimated about twice as many planets as there are stars. And then earlier this year, there was another study, and they found that there could be 100,000 times more rogue planets than stars in the Milky Way. So that's pretty crazy. But there was a new study out just this week, and they said that these kind of rogue wandering worlds could find a new home, possibly, and be captured into orbit around another star. And this would happen especially if the planet came across a star moving in the same direction and about the same speed. So again, as crazy as this sounds, the team said that this could explain some of the planets that are really far away from their stars, that normally there wouldn't be enough material out there to form a planet. Or it could explain another discovery that took place in 2006, I believe, without a star. So it's pretty crazy. And as for our own solar system, they said that there's probably no evidence at this time that our sun could have captured another world. They could definitely rule out large planets because we've seen them, but there's not a zero chance that a small world might lurk out on the fringes of our solar system that's actually from another solar system originally.
I just imagine the amount of the dynamics, the various interactions that would have to happen for all of that to line up, with one planet getting kicked out of one star, and then it's somehow getting captured by another star. It sure seems, I mean, not far-fetched, but I guess it's a great big universe and lots of things happen, right?
Yeah, I know there was a discussion on Universe Today on our article about, well, could this account for some of the missing matter in the universe? No, probably not, but it definitely sounds like there's more of these things out there than we've actually detected. So it's pretty interesting.
Yeah. Now, you had one other story that you wanted to talk about this week, and that was the how they're going to be attempting to capture, I call it capture a dragon, but what's the real story here?
Well, yeah, they are capturing the Dragon capsule forward to the upcoming SpaceX launch of the Dragon capsule. And why it's kind of interesting, or what's happening here, is that originally when the launch was supposed to happen in February, there were going to be the three astronauts up there were going to be Dan Burbank, Don Pettit, and Andre Kuipers. And so they kind of had a three-team tag team method of how they were going to do this. Well, now with the delay, Dan Burbank is actually going to be back on Earth by the time Dragon arrives, which is going to be, I think, on May 3rd. The launch is set right now for April 30th. Anyway, so Don Pettit and Andre Kuipers have to figure out and kind of basically redo their training, and they don't have access, of course, to the great training equipment and facilities that they have at Johnson Space Center. So they have to do all this training up at the space station. And they actually have one really good training method, is actually using the Canadarm2 that they have up there in the space station, and actually manipulating that and going through the motions of how they're doing it. But they also have a computer-generated kind of a simulator. And it was interesting, Don Pettit said that he has it set up so that it's ready to go at any time. So he gets up in the morning, grabs his bag of coffee and a cinnamon scone, and runs over to the simulator and does that every morning. So I think it's going to be really fun to watch. I'm sure there's going to be a lot of coverage on it, and I'm sure it's going to be on NASA TV. Hopefully they have good lighting conditions so we can watch them actually grab it with Canadarm2 and berth it to the Harmony node.
That's fantastic. Again, I mean, we've talked about this in past weeks, just how this stuff is all happening. Like, I think people have been really depressed by the wrapping up of the space shuttle, and we'll talk about that shortly. But all this is still progressing. I mean, you know, the fact that SpaceX, they're getting the Dragon capsule up into space, they're learning how to capture it. This is all proceeding still. So it's great to see that this, you know, some of these further steps are still happening.
Well, there was a teleconference for reporters yesterday that NASA had talking to the lead of the technology division and the space science division. And one of the reporters asked them, you know, well, what's new at NASA? You know, we're looking at all this old stuff going on, you know, the shuttle going on and stuff. And they said that there are probably 1,000 different projects or missions going on that have been initiated in just the past 2 years. And we've talked about that, about some of them. There's an atomic clock mission that's going to be launched in a couple of years, and laser communications and that kind of thing. So there are new things going on at NASA, and as you said, Fraser, it's, you know, things are kind of coming to a head and happening now as far as commercial space too.
Yeah, so in some cases, you know, people are worried about them doing old things, but sometimes it's important to do old things in new ways. And so, you know, launching a capsule up to the International Space Station, this isn't something that's never been done, but having a private firm headed by Elon Musk that's hoping to do this kind of stuff at a fraction of the cost, that is new and different and interesting. So I think that's still really, really important. All right, well, let's move on to Pamela, and you've got a couple of stories as well. So the first thing I think is the Space Shuttle Switcheroo that just was completed just a couple of days ago, with the Space Shuttle mated to the top of the 747 carrier aircraft and doing these low-flying passes over Washington, D.C. And, you know, my inbox was filled with people who were there and caught pictures of it, everything from cell phone stuff to these wonderful telephoto lens images. So that was fantastic.
Yeah, it's absolutely amazing, and it's only the first stage that has been done. Right now, major cities all across the United States are gearing up to have space shuttles arrive, and moving Discovery to Washington, D.C. was really just the first step. And there's these fabulous images, as you pointed out. There's one of it that Nancy's showing up on top of the 747 carrier that's being used, and so this spacecraft was piggyback rode from Florida up to Washington, D.C., did these fabulous flybys of the Washington Monument, of all the major sites, and the whole city turned out. Some of my favorite pictures were people actually standing on the roofs of the Smithsonian. So basically all the employees who had windows crawled out their windows, got on the roof to try and take in this spectacular event, and reports across the internet are of people basically shouting with joy as the space shuttle circled over.
I think NASA underestimated how important and how meaningful this event really was, and I think if they could have turned the clock back, they would have had them fly over more cities. You know, you can imagine it taking a tour from Florida to Washington via New York and Miami and
well, New York has one coming.
Oh, they do. Okay, but still, yeah.
Yeah, no,
and Vancouver Island would be nice too. But yeah.
Well, I think actually that might have been a little bit problematic because you have to turn the cities into no-fly zones while you're doing this.
Whatever. Who cares? You know, if that's what you got to do, that's what you got to do. The point is just it's such a meaningful thing, and it's a celebration of this wonderful spacecraft and the people who made the ultimate sacrifice in getting humans into space. I don't think they really. I mean, just to even think to do it over Washington was fantastic. Yeah. But I think that would have been a great spectacle. I'm sure a lot of people would have complained about the. Yeah,
one of the awesome things about this is Washington, D.C. is a no-fly zone unless you're Air Force One. And because this is being flown by military pilots who, let's face it, in order to be able to piggyback fly the space shuttle, you kind of have to have really high security clearance. So they were able to overcome all of the no-fly zones that were put into place after 9/11, get permission to get up close, personal, low down to the ground, and fly over the city that's filled with, well, people influential in the NASA budget stream. So let's hope that that has a great effect as well. Now, right now, at the Air Force Base, not Air Force Base, at the airport, that the Smithsonian houses all of their old spacecraft and airplanes and everything else. The shuttle Discovery is nose-to-nose with the shuttle Enterprise. Now, the Enterprise was used in drop tests. It was used in wind tunnel tests along with the shuttle Pathfinder, which is down at the Huntsville Space and Rocket Center, and no one seems to ever remember it, but there was another one. Enterprise was originally planned to actually be full-fledged space shuttle, but after all the testing and after all of the development in technology, they realized, wow, we can make things lighter now than we used to. Lighter means easier to lift into space. Enterprise never flew. Well, the Smithsonian, as you can imagine, they wanted a space shuttle that flew into space. So even though they've had the Enterprise for a number of years, they said, we want one of the real ones. So right now, they're getting ready to give up Enterprise. Now, it was supposed to be Monday that the Enterprise was going to get flown down to Kennedy Airport in New York City and placed on a barge and sailed up the Hudson to its final resting place on the aircraft carrier Intrepid. But right now, there's weather concerns, so that may not be happening on schedule. But I just love right now these two space shuttles that due to the differences in when they were built, probably never got near each other, are basically having their first meeting nose to nose down in the DC area. And this is probably the only time you will ever again see two shuttles in the same place. And it's pretty special. And it's really amazing just how easy it is to anthropomorphize these two spacecraft. And I love listening to the astronauts they have doing stories on this. One of the women who flew up on Discovery said that since it's one of the older spacecraft and has been flown a lot, there's just a lot of little touches that make it feel like going home. And so while living in the spacecraft, she always felt more comfortable there than she did in some of the other shuttles. So this is a very beloved spacecraft, even to its astronaut corps.
And yeah, absolutely. I think it's going to be fantastic, and I think NASA is right to celebrate it, and we will be helping to celebrate it in all of our various, outlets as well. So,
and I think that there are possibly some plans for when, let's see, which one is going out to California? Ian, do you remember?
Endeavour.
Endeavour, okay.
Yeah.
When Endeavour flies, it's going to be basically cross-country. So I think there are plans to stop at a few locations because they can't do it all in one day. So yeah. I'm hoping they stop in Illinois.
We are the halfway point. St. Louis would be perfect. The spirit of St. Louis. We have a big enough landing strip here.
Yeah.
So that's our shout out for St. Louis. Nancy, you're welcome in our house. Come down. All of you in the Hangout, not all of you listening to the Hangout. Party in St. Louis if that happens.
Sounds good.
Yeah. I've been definitely meaning to take the kids to Washington D.C. next. I think is one of the places we're going to want to go and see the shuttle for real ourselves. So that sounds great. All right, well let's move on. Now Pamela, you've got one other story, which is the end of dark matter.
Well, we don't know. So there's this intriguing paper and press release that came out from the European Southern Observatory folks. So there is a paper that's been accepted, so it's gotten through peer review. Getting through peer review does not mean something is true. It simply means you got someone to agree that other scientists should have a chance to read it. So the paper is co-authored by C. Bidden, G. Carraro, R. Mendez, and R. Smith. These are astronomers all down in Chile, and they've been working to try and understand the motions of 400 of the nearest stars. And the reason that they're doing this is all of our dark matter predictions, all of our dark matter models say that there should be roughly a Earth's worth of matter per reasonably measurable size of space in the local neighborhood. And breaking that down further into human terms, there should be about a kilogram to several kilograms of dark matter per Earth-sized volume. So when you start getting to big areas of space, this should be measurable. We should be able to detect it. dark matter doesn't interact via the electromagnetic force, therefore we don't see it with light. It doesn't absorb, it doesn't react, it just sort of sits there, and the only way we can detect it is via gravity. Now you'd expect, since when we look at the motions large scale of things within our galaxy, we're able to see objects that's motions are directly impacted by the theorized dark matter. And normally I wouldn't say theorized. So the issue is you'd also expect to see maybe motions on smaller scales where things are moving slower or faster than expected depending on the distribution of dark matter. And our ability to measure the motions of stars nearby just hasn't been up to snuff. We are limited in terms of our ability to measure three-dimensional motions in space, rely on us looking very carefully at Doppler shifting, how much the light of a star is shifted towards the red or the blue due to their motions forward and backward, and our ability to actually measure over time the shifts in position of stars moving across our sky. That's an extraordinarily difficult measurement to make. And due to limitations on our ability to make those measurements, we haven't been able to say at small scales whether or not that dark matter can be seen affecting motions within star clusters within local groups of stars. Well, this group has detailed a new way of trying to sense out the motions that are going on. And they have 3 pages of equations that I haven't fully made it through yet. But they've defined a completely new technique for getting around these difficulties in making measurements and trying to say whether or not dark matter can be detected. And they claim that based on their completely new way of looking at motions, they have eliminated the possibility that there's dark matter within that region of space at a significant level. They can't completely rule it out, but they can rule it out at a significant level that matches any of the predictions. And this, of course, is entirely pressworthy because they're basically saying that with an error of 4 sigma, and with science you really want 6 sigma or better, but with basically a 2/3 the amount of error that you're hoping for, but still not that much error, they've eliminated the need for dark matter. Now, I want to place a huge number of caveats on top of this. They have defined a completely new technique. The fact that this paper is getting published is a way of opening a dialogue, opening a discussion. It's not a way of saying this is 100% true. It's a way of saying, okay, other people out there, we've done this math. Look at our math, tell us what's wrong, what's right, and let's start this discussion over whether or not we actually still need dark matter. Now, I personally look at this and I'm like, okay, you've done math. That's all very good and very nice. But what they haven't done is explained why do we see all of the observables that point towards the existence of a particle form of dark matter. They haven't explained the microlensing that's seen in clusters. They haven't explained how we see clusters merging. There's a whole lot of things left out. What they've done is simply say, we can't observe dark matter within a galaxy within this 400 star sample that we've looked at.
Right.
So lots and lots of caveats, but it's always good to see scientific discussion started in the journals. And there's, of course, a press release to go with this because it's fun to say dark matter doesn't exist.
And as you said, this is exactly how you want science to work, right? Which is some people will come up with a way to, I'm sure when they started out, they thought, well, if we can observe dark matter at these galactic levels with the microlensing events and things like that, maybe we can observe it at some kind of local level. Yeah. Let's find some situations where maybe stars should be getting tugged by local amounts of dark matter, and let's try and measure it and to try and provide more parameters for how dark matter is going to work. And then you can see they don't find it, and that discovery is just as interesting, or that as if they had discovered or put constraints on it in measurements. And it's nothing personal. It's just like, here's what we found. feel free to integrate that into what you guys have discovered, and let's get towards an answer of what this phenomenon really is. If it isn't a particle, then there's going to need to be some explanation for the other things that have been observed. But the whole process moving forward is great. And it doesn't mean that science is wrong or science is stupid or any of that kind of stuff. It's just how the whole process works.
It means science is a dialogue.
Science is complicated.
And we're always looking for exceptions. I mean, when you're trying to say a particle exists that we can't detect except through gravitational lensing and movement of objects, that's a pretty profound statement, saying that there's a particle that doesn't really interact via the forces everything else interacts with. And so you have to bang away at that theory with every possible hammer you have, and it's only when that theory doesn't break that we accept it as true. And this is just another hammer to bang down on our theories of dark matter.
Yeah, no, I think it's fantastic. All right, well, I think we're out of the stories that we want to talk about, and we wanted to take a couple of questions. Now, there was one that came on the Twitters, and I guess this is for Ian. Does the from Icarus Factor, does the plasma from a solar flare convert all of its energy to extending magnetic fields or a high temperature stream as well? I don't know if that makes sense to you, Ian.
Yeah, I think I know. Basically, we don't know. I think what he's referring to is that, where does the energy go from these explosions? I mean, do they go into heating? Well, the plasma is already hot, so does the energy from that go into expanding the magnetic field surrounding this coronal mass ejection? And we don't really know. We don't really understand the energy budget in the lower corona yet. And the main reason for that is that we haven't got a probe in there. We can't directly measure it. And it's a bit like, we're trying to find these alphane waves, as I mentioned earlier. The biggest problem with that is we haven't sent a probe into the lower corona, and we can't. I mean, until Solar Probe Plus launches, I think it's in 2018, which is going to go astoundingly close. I mean, it's like 5 or 6 solar radii, something ridiculous in the deep corona. And this thing's going to go in and actually take direct measurements of the plasma environment. Then we'll start having some answers, because at the moment we're depending on the observatories that are on the Earth. We've got some very, very sophisticated observatories here, and we've got sophisticated observatories orbiting Earth, and also orbiting the Sun. We've got the stereo spacecraft that are going opposite ways around the Sun at the moment. And so we've got a very good remote view of the Sun, and that is where the problem is, because you're looking through the Sun's atmosphere. So there's a lot of interference along the way. So there's a lot of very clever tricks we need to do as observers to actually decipher what mechanisms are going on deep in the corona. And actually, I've just managed to get this video. I just wanted to show you this coronal mass ejection. I was trying to share the screen.
Well, I think Pamela has always described your branch of physics as possibly the most was it solar hydrodynamics? I don't remember the title for this.
Magnetohydrodynamics.
Magnetohydrodynamics. So essentially, it's the most complicated math out there, and so it's not surprising that the Sun is giving up its puzzles very, very slowly.
I just love the violence involved in this.
Yeah. You want to play that one more time, Ian?
Yeah, it seems to be, I don't know if it's going as fast for you guys. It seems to be going slow for me. But yeah, as you can see here, you'll see that the explosion happens, and then you get all this plasma raining back onto the Sun, which you don't usually associate coronal mass ejections with. You always think it's a massive explosion pushing out into interplanetary space. I think. Did it work? It might have worked. I didn't fall off.
It worked the first time and it didn't work the second time, but don't worry about it. We're just going to tell people to go to your page. Yeah,
go to the page. But yeah, basically we're just understanding the dynamics of the lower corona, and it's only with the help of the SDO really in recent years that has really opened our eyes, because we're seeing these very small scale structures, and as Pamela said, the magnetohydrodynamics, which basically means magnetic flow of plasma. That's basically what it means. It's the science behind the hydrodynamics of plasma in the Sun. It's horribly complex. And to be honest, I only scraped the surface of it when I was doing my PhD. I only looked at a very small subset of the equations. But the equations went on for pages. And if you have a look at my thesis, I think the equations go on for 20 pages. And it's just not pleasant. And you have to program all that into your program. And to be honest, I look at it now, and it's like a foreign language now. I've completely forgotten it.
Foreign language that you used to understand.
I used to be. I wouldn't say fluent. No,
You could speak.
I could be hand waving and say, yeah, this equation does this. That was about as far as it went. Yeah. But yeah, it's fascinating, and we're only just beginning to see these theorized structures in the lower corona, and we're able to resolve them to, you know, a few tens of kilometers wide. I mean, that's just ridiculous.
Yeah.
So it's amazing. But we need to send a probe in there, and hopefully Solar Probe Plus will be the probe to do that.
Now, John McKinney wanted to know, I guess this was a question about the rogue planet. He says, since the rogue planets are small, relatively small, dark, and distant, how were they ever detected from Earth? So, for Nancy, I guess it's not that the planets have necessarily been detected.
Oh, he's back again.
Hey, wow, that worked. I don't know if this is... Oh, it says it's still being broadcast. I have no idea. I think it is. Did you get the question there? This was Nancy about the rogue planets.
So what was the last part of it?
I'll do the question. Since the rogue planets are relatively small, dark, and distant, how are they ever detected from Earth? So, and I guess the point here is that it's not that they're necessarily being detected, right? It's just that it's an explanation for where they might have come from.
Well, the one study did actually detect about a dozen of them, and they did it through microlensing.
Right. Are we having technology fail now?
I'm trying to figure out if we're still broadcasting. No one has responded to my request that they please. I'm seeing it after I refresh the page, according to Mike Perry. So hopefully people will know to refresh the page. I don't know if this means that our embed code changed.
Oh, I don't know.
So well, So Nancy, keep asking, and I'll work on the technological problems. If you see my eyeballs going everywhere, you now know why.
Well, I think at this point, then I got a bad feeling. I got some bad feeling about the way the technology is going, and I think we're kind of nearing the end of this anyway. So why don't we wrap this up, and hopefully it'll all get stitched together. And if not, we'll do it after the fact. So whoever can still hear me, thank you very much for joining us this week, and thanks to Ian and to Nancy and to Pamela for joining us for this week's Hangout. And we will see you. We'll see you all next week. And we've also got all of the other stuff coming up as well. We're going to be getting back to our virtual star parties, and we've got more recordings of Astronomy Cast coming out, and other the weekly science hour. So there's a lot of great stuff coming out from across all of the CosmoQuest group. So thanks again, everybody, and we will see you all next time.